everyone, my name is Aleta and I'm working with Blue Front Solutions under the guidance of Hatch Engineering in the production of blue ammonia, or ammonia production characterized by a high degree of carbon capture. So more specifically, our goal here is to design a plant capable of producing 1,000 tons per day of ammonia from natural gas, while reducing the carbon intensity from the conventional value of 2.4 kilograms CO2 per kilogram NH3 to less than 0.1. So considering this high conventional intensity, as well as the forecasted annual growth rate in ammonia demand, it's not difficult to see the motivation behind this project. The emerging market for ammonia use in hydrogen fuel transport really contradicts the intention of using hydrogen fuel if the ammonia is not produced by a blue or green process. So the front-end production of syngas to obtain the required hydrogen is the main source of CO2. The focus of our design solution is reducing these CO2 emissions right off the get-go, so reducing the amount that needs to be captured. The partial oxidation reaction shown here is really what allows us to do so. Capturing carbon requires energy, which counterintuitively emits more carbon. So the use of an oxygen-fed partial oxidation autothermal reformer allows us to eliminate an entire carbon capture unit at this stage. So my main area of focus for this project has been designing the front-end reactors required to produce hydrogen, which are the main sources of CO2. The common process I've used to design the 4 reactors listed takes place in MATLAB and begins with the application of differential material, energy, and momentum balances. Because it's not feasible to validate these results experimentally, all results have been validated against simulations done in literature. So once similar trends are confirmed, I begin the iterative design process of manipulating operating conditions and sizing parameters such to optimize energy requirements and outlet conditions. So although there are different considerations for each reactor, the process and reasoning is more or less the same for each. So for the sake of time, I'll focus on one reactor, that being our pre-reformer. The purpose of this unit is to convert all higher alkanes in our natural gas feed to methane via irreversible reaction 1 and the reverse of reaction 2. So this unit also jumpstarts the production of hydrogen with forward reactions 2 and 3, which are steam methane reforming and water gas shift. The motivation behind converting these heavy alkanes is to prevent coke formation and normalize the steam and temperature dependencies of natural gas in the key partial oxidation reaction, which takes place downstream. So because irreversible conversion of higher hydrocarbons is known to occur very quickly, it's of common practice in literature to base kinetic models on presented reaction rates 2 and 3. So note that rate constants K2 and K3 follow the Arrhenius equation. The reaction takes place in an adiabatic packed bed reactor. ODEs shown are based on the utilized mass of nickel catalyst packed within these tubes. So the momentum balance used to determine pressure drop is based on manipulations of the Ergun equation. The adiabatic energy balance is based on enthalpy, heat capacity, and rate expressions for each reaction. And lastly, the mole balance depends on stoichiometry of each species given by alpha, as well as the rate expressions, which are temperature and pressure dependent. So after validating the system of ODEs, the iterative design process began with varying one of inlet pressure, temperature, and steam to carbon ratio, while holding the remaining conditions as well as sizing parameters constant. To illustrate the thought process involved here, I've included a MATLAB plot resulting from varying steam to carbon ratios. So although adding more steam increases the conversion of methane, increased steam and net flow rate through each tube also significantly increases the pressure drop. So because we intend to use a single compressor at the front end of our process, conserving pressure in this upstream reactor outweighs the benefit of increased methane conversion, especially because methane is further converted in subsequent reactors, whereas our process stream cannot be repressurized without another compressor and more CO2 emissions. So it's important to note that simulations were conducted for a single tube, meaning the number of tubes dictates flow rate through each. Other sizing parameters to consider are tube dimensions. Here we can see the example of varying tube diameter, again on methane conversion and pressure drop. Larger diameters minimize pressure drop and allow equilibrium conversion to maximize, with the trade-off of increased catalyst requirements. So to balance the benefits of increased conversion and pressure conservation with operating costs, this case eventually led to reducing the length of a reactor, such to reduce our required catalyst mass. So hopefully this presentation has been informative and interesting for everyone. Please do not hesitate to reach out should you have any questions. Thank you.